It's advanced SQL and array time again. Welcome back to our discussion of the array data type in PostgreSQL. Okay, so what we'll see in the upcoming slides is no surprise at all because it just concerns the operations that you would expect any system to have when it supports an array data type, namely constructing arrays, then accessing arrays in using positionals. Position information, that's the prime operation, the prime access operation for arrays, array indexing, and then also operations that allow you to search among the elements inside such an array. That would not be positional access, but access by element content or element value. So let's see what PostgreSQL has in store here. Right, so given a particular array, we would certainly be interested in how we could append further elements to such an array, or prepend further elements to an array. Array positions, array ordering, element ordering is really essential. So appending at the end or prepending at the beginning really makes a difference. And indeed, there are operations inside PostgreSQL which can do both. And they are appropriately named array, array prepend and array append. Okay, so the array that we are appending or prepending here is being designated by this particular funny symbol so that you can easily spot it in the constructed arrays. So array appending, would append this particular array element at the end, and array prepending would put it at the beginning. And that indeed should be this funny symbol and not the X here. I'm sorry about that. Will be fixed in the downloadable slides. When you got two arrays already specified as the n element and the m element arrays here in the arguments of the array cat or the array concat operation, then this operation would do exactly what you expect. It would just glue the arrays. The first argument would supply the first elements. The second array argument would supply the trailing elements in this glued array, and together the element would have n plus m elements. So that's the array concatenation operator that you would probably also expect. All of this is good and well, but there is a very elegant, very efficiently typed, because it's brief, operator-based notation for all of these three operations above. It's this double pipeline symbol operation which suggests that something is glued to something else. So you would have infix notation with this double pipeline symbol operator, and as you can see, it's very flexible. It's really overloaded. It can expect single elements as the second or first arguments, or it can operate over entire arrays. XS and YS are supposed to represent arrays here. And they are doing exactly, these operations are doing exactly what you expect. So because it's so brief and so elegant using its infix notation, you will see many of our examples use this very lightweight notation of using this array concatenation operator in its polymorphic overloaded form. Okay, so much about constructing arrays. Accessing arrays, of course, is the prime operation that you would expect from an array, and you would expect efficient support for positional access. This is the main characteristic of the array data structure. And of course, PostgreSQL does support that. We can have array indexes which are integers, and as I told you, these array indexes are starting at 1. Okay, so 1-based indexing. So in the slide below here, let XS denote an n element array of these xi elements. All right. So accessing, of course, at index I would represent xi. Okay. If you would access this array outside its defined bounds, so if you would use an array index that lies outside this well-defined set of array indices, you would receive null if you perform such array indexing here. Okay. So that's semantics of array access in PostgreSQL. You will get null if you access elements outside the actual contents of this particular array. All right. accessing contents of a null array, so XS might for some reason be indeed null, will yield a null value, just like accessing an element at the null index will return a null value. I think all of these are quite reasonable definitions and behaviors in a language that is equipped, in type system that is equipped with null values. All right. Okay, then there is batch indexing, or slicing as it's sometimes called. So retrieve all the elements between the indices I and j inclusively. That will give you an array of the respective elements. All right, we expect I to be less or no more than j, no greater than j. If this should be the case, then the slice, the array slice, the extracted slice will be empty. You can have open-ended. You can have half open slides like this slide that slice that extends to the very end of the array, or this slice that extends to the very start of the array. All of this should be really intuitive and should behave just like you would expect it. Okay, so how would you access the last element, for example, in an array? Or how would you generally determine the length of a given array? And that would be the job of the array length function. The array length function would look at the first dimension of the length of the first dimension of the array XS here, and would return the number of elements in that first dimension. Recall that an array in PostgreSQL might be multidimensional or rectangular. So each of the dimensions would have a particular well-defined array length because of the rectangular restriction. Okay, so this second argument 1 could also be used to look up the array length, the dimension of a particular array XS in the second, the third, or the nth dimension. Okay, all right. So, and combining this with array indexing will of course access the last element of XS, just like we were wondering above here. Okay, there's a different function that looks for the number of elements inside such an array. And if this array is one-dimensional, the number of elements in such an array is just the length of an array. And this is done by the cardinality function. But if XS, the array XS would be multidimensional, then cardinality would return the sum of elements in all dimensions. So please be aware of that. For one-dimensional arrays, this is just a very nice alternative notation for the length of the array. Otherwise, it's really the cardinality, the number of elements in all dimensions. So in a rectangular array with n times k elements in 2 dimensions, the response of cardinality would be just that, n times k. Okay, nice. So a rather complete support for array indexing and array length measuring in PostgreSQL. That would be indexing and slicing. That's what you would expect from language supporting array operations. But there's also the other mode that I was mentioning of accessing the contents of an array, and that would be searching the array, searching for particular element values and extracting these particular element values from inside an array. Okay, so to demonstrate this, consider an array XS again with n elements, but let's be very specific and say that at indexes I and j, there's this one particular funny element stored. So we know the value of the element at indexes I and j, it's this funny value. Okay, all right. So so let's look at this first. So if you look for this particular funny element value inside the array XS, then array position can do just that. It will scan the array XS, will look for the first occurrence, for the leftmost occurrence of this specified value, and then will return the array index, which is I in this particular case. Okay. Should the value not be found, we get null. Okay. If there are more occurrences of this value inside the array, just use array positions. Notice the trailing s here in the function name. And the array positions will report all occurrences of the search for value in array XS. And for the array above, we would get 2 hits, 2 locations at which we can find this particular funny element value at locations I and j. If there is nothing to be found in XS, then the answer would be the empty array of indexes. All right. We could also use functions in the PostgreSQL array library to replace occurrences of this funny value by this other no less funny value. Okay, and the output of this operation would be just what you expect. At element indexes I and j, this other funny value would now take the place of the diamond-shaped value. All right. Okay. More general forms of looking up and searching for particular contents in an array are provided by existential and all quantifiers or universal quantifiers that are supplied to us. And this is a very flexible way of searching for things in an array. These will return a Boolean value to us, and the Boolean value is determined by in the case of the any or the existential quantification is determined by the presence of any element inside array XS that is in tether relationship to X. So tether might be any of these well-known comparison operators. Maybe it's equality, but it could be one of these inequalities. All right. So if theta is equal, the equal sign, then this would return true according to existential quantification if there is any element, if there exists any element in XS that is equal to X. This would return true if all elements in array XS are indeed equal to X. Okay, so these are two quite powerful operations that allow you to express quite some sophisticated searching inside the elements of an array. What you will get back and what you get returned here are Boolean values. So these are really suited to be used in predicate positions, for example, in your where or having clauses of your SQL queries. Okay, so let's switch over to the terminal and see how these could work in practice. Recall our table of encoded trees. So I've got the table trees again here. So let's dump it again. This is our table of 3 encoded trees, or to be more precise, of 3 encoded forests, because we knew this is indeed a forest of 2 root nodes. Okay, so we will find the parent and the label information stored in these ordered arrays inside our tree encoding. Okay, and as I told you, corresponding positions inside these arrays, for example, the second position here, the B label, corresponds with the second position in this parent's label. So the parent, the node with index 2 is labeled B and has parent 1. Okay, so it's very important that the length of these 2 arrays are in sync, that they are equal. Each node should be supplied with label information. Each node should be supplied with parent information. And that's of course true for all of the rows that we have in this trees table here. This query would check just that. Are all the parent and labels arrays inside each of the rows here, are they of the same cardinality? Because these are one-dimensional arrays, cardinality is equivalent to just looking for the length of these particular arrays, the cardinality, the dimensionality in dimension 1. Okay, so for each of the trees T, we would just check that. We would check the cardinality of the parents and of the labels array. These would yield natural numbers, and if these are equal, then everything is fine. Then both parents and labels arrays have the same number of elements, and we would just aggregate the Boolean values that we see returned here by this bool and aggregate function. It's a Boolean aggregate function, just like a universal aggregation. If all of these tests go well, then the Boolean AND will return well or true. And that's indeed the case. Why did it do so? Because all of these comparisons turned out true 3 times. Why did that come out true? Because all the cardinalities are the same for all the parents and label arrays stored inside our trees table. Okay, so let's repair that. Okay. So using all of these functions and operators to search for contents in arrays, we could answer questions like, hey, which trees and in fact which nodes carry an F label, inside my trees. And there should indeed be, let's scroll back here. That should indeed be 2 trees reported, because these 2 trees contain at least one node that carries an F label. In tree 3 there is no F label. All right. So which trees and nodes carry an F label? So there should be the trees 1 and 2 reported. Let's see how that goes. So we iterate over all the trees and look at the labels, at the labeled arrays that we see down here in all of these trees, and then check if any element, any label inside these arrays is equal to F. Okay, so this will yield true if any of the labels inside the labeled arrays compare to F and yield true. Okay, this should be the case for the trees 1 and 2. Okay, these true trees, the identifier of the 2 trees would be reported, and we would also report the position. We would also report the position, the node number of the F nodes. We know that we will indeed find such an F node inside the labels array. So array positions here will never report an empty array. It might indeed report multiple node indexes if there are multiple nodes having an F value. Let's check. Okay, so trees 1 and 2 are reported as we expected, and there are indeed only single F nodes in each of these 2 trees. This is the result of the array positions function, and it would report the array indexes 6 and 2 as expected. Okay, so another example, find the label of the first root node inside each of these trees. First root makes sense because we are talking about forests here too, and some of these stored forests might have more than one root. We are talking about the label of the first root. Okay, so let's iterate over all the trees and indicate which tree is currently being operated on. And then inside the parents array of this of a tree T, we will look for null entry, for the first null entry actually, because we are using the array position function. We look for the first null entry inside the parents array. This will be stored at the position of the root node. This will be the index of the root node. Okay, we use that index to look up its label in the labels array of tree T. We know that the positions in the parents array and the labels array are in sync. We can use this reported root array index to look up its label in the labels array and find the labels of the root nodes, of the first root nodes. So AGA, let's see, I think I brought, yes. So this is the A in the first tree. This is the A being reported in the third forest. It's the first root. And this is the G label of the root in the second tree. Looks good to me. Okay. Finally, let's find out which of the encoded trees are indeed forests. So which of these encoded trees have indeed more than one root node? Okay. That's also very easily done. So let's iterate over all the trees. Each of these could be a forest potentially. And then look at the parent information and see how many null values we can find in the parent information. Okay, so let's look for the null values. Let's search for the null values. Okay, and be sure to report all of the null values. So use the array positions function again. This will report an array of indexes, the indexes at which null is to be found. This will report an array. If this array contains more than one entry, then there is more than one null value to be found among the parent information. This is what characterizes a forest. Okay, so T3, the third entry inside our forest and trees table, is indeed a forest, as expected. Works out. Okay, so this is already something that we can do with our arrays, and in this case with our array-based tree encoding, but I could easily imagine a lot of more operations, queries, problems I would like to formulate and evaluate over my tree encodings. I would like to find the largest label, for example, in a tree. I would like to transform all labels to uppercase. Currently, all labels are lowercase values. I would like to transform all of these to uppercase. I would like to find the parents of all nodes with label C. Okay, so I think I could identify the indices. I think I could identify the indices of the nodes with the label C using the array positions functions, but I would then need to take this array of indices and look all of these indices up inside the parents array to find the parents of these nodes labeled C. So I would need to iterate over the reported C indices here. Here I would need to iterate over all the labels to identify the largest label. Here I would need to identify over all the labels to transform them into their uppercase variant. So in general, I would need to have a way to access all of the elements inside an array and then iterate over these elements. And that's not easily done. It actually cannot be done with the operations that we have described so far. I would also like to do some structural reconfigurations or operations on my arrays. For example, I would like to glue one tree to another. I would like to glue the root of one particular tree and glue it to a second tree, just like described here in this point 2 here. This would of course need some reconfiguration in the parents area. I would need to glue the parents and the labels arrays together. I would need to do some updating, some shifting of values in the parents array, because nodes are now being stored at new positions and need new parent information. All of this should be possible with the operation that we have described so far with the array operations, but it's really not. We need something else. We need something more. We have so many cool stuff already at our hands to do to work with arrays, but it's not yet sufficient. We need something else. Okay, and we need not much else, but a very crucial bit is still missing. And we will address this very crucial bit. It's really the bridge between relational and tabular data in the upcoming video. See you then.